We're like missing a bunch of people.
Not really,
All right. So we're going to go ahead and write binary to decimal and decimal to binary. Then we're going to start talking about objects. We actually started writing an object. We started talking about objects last time, but I think I kind of implied to write these as just the static methods. If you wrote it inside of an object, that's fine, but that wasn't required. All right, so binary to decimal takes a string representation of a binary number, converts it to decimal, returning the answer. So for example, if we pass in the string 1001, it should spit out the integer 9. So we're going to have a static method. It's going to return an int called binary to decimal. This guy's going to take a string as a parameter. Maybe I'll call that guy bin. It's the binary representation. All right, and it ultimately needs to return an int. So now, for example, if we have the, well, we'll just do it with this. This 1 is in the 1's place, 2's place, 4's place, 8's place, or this is the 2 to the 0's place, 2 to the 1's place, 2 to the 2's place, 2 to the 3's place, right, as we walk from right to left. So we're going to have to keep track of what place we're currently in. So we always start off at our place. The far right is always going to be the 1's place, no matter what base we're working with. Base 2, base 8, base 10, it's always going to be the 1's place. Binary is base 2. So as we walk to the left, we're going to be multiplying it by 2. This is the 1's place. Times 2 is the 2's place. Times 2 is the 4's place. Times 2 is the 8's place. Okay? So we're going to have a, and then what do we do here? So this is 1 times 1, which is 1, plus 0 times 2, plus 0 times 4, plus 1 times 8. So 1 times 8 is 8, 1 times 1 is 1, 8 plus 1 is 9, that's why we should get a 9. And the 0 times 2 and the 0 times 4 will always be 0. So we're going to walk our string from the end to the beginning. So this is that loop, kind of like reverse string, same pattern as reverse string. So for int I is equal to bin dot length minus 1, so that's the last legal position in my string. Keep going as long as I is greater than or equal to 0, because we also want bucket 0. Subtract 1 from I each time. Now in here, we're going to ask the question. We want to know if the character we're currently looking at in the string is a 1 or a 0. Okay, now we know how to get an individual char from a string, right? We have a function called the charat method that allows us to extract a specific bucket. So we want to look at the character in bin at position I and say, is that guy a 1? If it's a 1, I want to do something with it. If it's a 0, 0 times anything is going to be 0, so we can just ignore it, right? So we'll ask if bin dot charat I is equal to, do I write it like that? Why do I write it like this? Almost. It's a char. Yeah, strings of the double quotes. This is the, I want to know if the, so charat returns a char primitive type. I want to know, is it equal to that char primitive type? Now, let me ask you this. Am I okay to use double equal sign? We talked about that last time, right? About how to compare strings. First of all, this is a char, not a string, right? But at a glance, it can look like a string, you know, so that's why you've got to practice on really resolving what you're looking at down before you jump to conclusions about the code. The double equal sign, this is the equivalence operator, but what does it work for? Primitive types. Okay, this is the equivalence operator for primitive types, which is why it doesn't work maybe as expected for strings. Okay, we saw last time. When I'm comparing two strings using the double equal sign, what's it actually comparing? The memory addresses of the strings, not the contents of the string. So the primitive value of a string is where it lives in memory. All right. But in this case, this is what I have on the right side is the char primitive. What I have on the left side is a function that ultimately boils down to a char primitive. I'm saying, are these two char primitives equivalent? This works. This is a perfect use for the equivalence operator. Okay, so if the character I'm currently looking at is a 1, then I'm going to go ahead and I need to have a running total here. So I'll have a sum started off at 0. And I'll say sum equals sum plus place. Because 1 times place will be place. So whether I've grabbed something, whether I've added something to my sum or not, I still need to change my place as I walk left in the string. So place is going to become place times 2, since we're dealing with binary numbers. After we've gone through the entire string, go ahead and return sum. So binary to decimal, we start at the ones place. Our sum is currently 0. Walk the string from end to the beginning. Each place along the line, if the character we're currently looking at is a 1, go ahead and add the current value of place onto our sum, storing the result back in sum. Regardless, double place each time. So place goes from 1 to 2 to 4 to 8 to 16, so on and so forth. Do that until we've run out of characters in our string. In the end, return our sum. So we should be able to call this guy. Is this a class method or an instance method? Class method. How do you know? How do you call class methods? So driver dot. Let's do this. Well, we'll just print it. Driver dot binary to decimal 1001. So this is a good example of a line that unless you actually break it down, you might not realize exactly what it's doing. So this is a function call being called by the name of the class. So this guy's probably a class method. So I'm calling my method here, passing at 1001. That guy's ultimately going to boil down to an int because that's what that function boils down to. So everything I have highlighted right here ultimately will become an integer. And what am I doing with that integer? I'm printing it. So this should give us the 9. Root. Oh, this is in my driver or my dice class. Oh, show pass by value stuff. Told you I was going to put an error in there to remind me. So now somebody else has to remind me after I test this. All right, so there's my 9. Okay. Questions on binary to decimal. So let's look at decimal to binary. So decimal is going to take in an int and spit out a string. So static string decimal to binary int des. Elevate that on the screen some. Okay, so what we're going to do with this is we're going to divide it over and over and over again by 2, recording the remainder. So if we go and do this, we have the string, what is that, 1010? Is that my example? Oh, actually, no, I'm taking it at 10. It should be what it spits out. So I'm taking in a 10. So a 10, yeah, that's good, divided by 2 is 5, remainder 0. 5 divided by 2 is 2. 2 times 2 is 4, remainder 1. 2 divided by 2 is 1. 1 times 2 is 2, remainder 0. 1 divided by 2 is 0. 0 times 2 is 0, remainder 1. And then we read our answer from bottom up. So 1010 is our answer. We know we're done as soon as we've whittled our original number down to a 0. Okay, as soon as our division becomes a 0. All right, so let's just do one move first, and we'll wrap it inside the loop. So our very first value is going to be the remainder of the integer division. So if I say, let's create a string called answer. We'll start this guy off as the empty string. And the very first thing I would do is I would say answer. We'll just do it backwards first. Answer equals answer concatenated with. I want to concatenate it with a the first remainder. That remainder would be decimal mod 2. Now I do need to make sure that after I've recorded the remainder, I also say decimal is equal to decimal divided by 2. I get the integer division. So I can keep weeding that down. So, and this is only going to work for positive numbers. We could always do some sort of error checking thing here and say if des is equal to 0, just return the string 0. You didn't have to do that if you didn't want to. You can assume they gave you something bigger than 0 just for the logic. So this would be our special case. If they gave us a 0, just return the string 0. That's the binary representation of 0. Otherwise, we're going to do some stuff. What are we going to do? We're going to create an answer. We're going to say while des is greater than 0. Go ahead and tack on to my answer, my remainder, and then go ahead and divide my decimal after the fact. I need to make sure I do them in that order because when I change des here, des divided by 2, storing the result back here, now I'm modifying des, so des mod 2 won't necessarily give me the same value. So I need to get the remainder first, then change the value. So as long as des is greater than 0, do this over and over and over again. What happens when des finally is equal to 0? Have I already recorded my final remainder? I have because I'm doing remainders first. All right. Are you going to talk about it being backwards?
Yeah.
Yeah. So we're going to go ahead and print this out. So well, I'm going to return it first, then we'll print it out. So I'm going to go ahead and return my, well, actually, we'll return it inside of this else since that's where its scope is. So really, this is the logic for the assignment. If you didn't wrap it in this special case if statement, that's fine. All right, so we're going to build this up. We're going to try passing it at a 10, and we're going to see our answer is actually 0101. It's going to give us our answer backwards. All the right stuff is there, it's just in the wrong order. So 0101. We really want it to be 1, 0, 1, 0. So one thing we could do is if you already had written this function before, you can call your reverse function, right? Just reverse it. Seems like maybe a little bit of overkill. The other thing you could have done and probably should have done is considered how you were building your string and just build your concatenation backwards. Remember, this plus sign here will be treated as the concatenation operator as long as one of the two sides, at least one of the two sides, is a string. So even though this guy is going to be an integer, since this guy's a string, it will concatenate this integer onto the front of whatever answer currently is. So we'll just build it in reverse. That make sense? All right, questions on that one? All right, so let me throw that code up on Slack. All right. Now, what if I wanted this binary to decimal to actually work for octal to decimal instead of binary? What would I have to change? I changed my variable name, so I have to change that a little bit. I didn't have to do that. It just made more sense. Only real logic changes right there, right? Multiply by 8 instead of by 2. Identical pattern exists for converting to from any base to decimal. But is this if statement good enough anymore? Because what are the legal octets in an octal number? 0 to 7 are the legal octets. We call them digits, but digits is actually base 10, so octets would be. Okay, so 0 to 7. Now, we can treat zeros the same way as we did in binary. 0 times anything will be 0. But now I need to deal with 1s and 2s and 3s and 4s and 5s and 6s and 7s. Do I just write more if statements? I could, right? For for octal, maybe that's not the end of the world. Writing more if statements, not that many, but certainly as we start getting up to larger bases, that's going to become more and more unreasonable. So with some of the magic tricks we've learned recently, what can I do here to get me the integer value of the number in the string? So I want to know what is the integer value of this guy, rather than saying, is this guy equivalent to the integer represented by that character? I want to know, is that guy the number 1? Is that guy the number 2, the number 3, the number 4? So this is what I want. I want a function that returns the integer version of whatever char was passed in. How can we write that? Somebody else for a minute. What tools do we have laying around in our Java toolbox right now that you suspect might be helpful for this? The inputs.
Or the imports.
Okay. I don't know where you're going with this, but we'll let you. You know, that's it. We're at the end. We're at the end. Go ahead.
The one that goes column which shows you the place in which
Index of.
Yeah.
Oh, so we got this like weird looking tool, right? How can we use index of here?
You have a string that has like 0, 1, 2, 3, 4, 9, A, B, C.
Let's just start with that. I think you're.
And it would tell you the index of like 0 would obviously be at bucket 0, 1 would be at bucket 2.
Just like that. Where is the char 0 found? At what bucket? It's found at bucket 0. The char 1 is found at bucket 1. Char 2 is found at bucket 2. Char 3 is found at bucket 3. I mean, I had to put them in that order. So because of how I formatted this string, I can now use this index of tool to search for, well, to convert a char 1 into the position 1, the integer 1. Does that make sense? Okay. And then as he pointed out, we start getting into hexadecimal, where we have the A through F. A lives at bucket 10. B lives at bucket 11, bucket 12, 13, 14, 15. Does that make sense? So we can actually convert any char that makes sense in our conversion chart thing into its integer equivalent. And that's going to be helpful for us. So if we're going to use this guy for, we'll leave it like this for right now. Actually, for octal, we only actually need it up to the 7. We'll fill it back in a little bit. Okay, we only need it up to the 7, though. So rather than have this if statement down here, we're going to say sum is equal to sum plus place times driver dot get int from character oct dot char at I. So this will get us our integer version of whatever character we're looking at, including a 0. So now we're actually going to do the math on zeros. We'll multiply place times whatever that number is. If it was 0, place times 0 will be 0. We'll add 0 onto our sum. Sum will be what it used to be. No harm, no foul. Okay, otherwise, we're always going to multiply place by the integer version of the char that we're looking at. And then we'll multiply place by 8 because we're doing octal. That make sense? Same thing's true here if we want to write this as base to decimal. So 8, 9, okay, so we got the whole alphabet in there. I think this lets us deal with up to base 37. After that, we've run out of things. Why would we even use larger bases? What would be the benefit of using base 20 over base 10? Go ahead.
It allows you to store a larger amount of data in a kind of more compact form.
Okay. So base 20, a really big decimal number would take up less space. That make sense? And conversely, a really big decimal number would take up even more space in binary. So why do we use binary? Is it simple? How many of you would prefer to count in binary than decimal? No takers? Just do everything in binary for a week. It's like a
Write our homework in mind.
We'd lose majors pretty quick. Well, unless we had you write the conversion program first, where you just feed your paper in, converts it right to zeros and ones, no problem.
And there's also like thousands of sites we can just copy paste that too, but making it yourself is much better.
That'd be a good way to screw with an English teacher. You know, like a 10-page paper, convert it to binary. She hands it back like, I don't even understand what's this crap. You get that like, whoa, I didn't plagiarize this. Can't you even read this? You didn't say it had to be.
A 10-page paper in binary, it would be way.
It'd be ridiculous.
It'd be, yeah.
But not necessarily inaccurate.
I wouldn't want to blow all those credits.
So I guess here this is a cheating strategy you don't want to follow. Is you're gonna cheat on a paper, you're gonna plagiarize it. Convert it to binary first and hope that the teacher doesn't know binary. That way you can at least make the argument that yeah.
Like, technically you only have to be like half a page back.
Exactly, yeah. Half a page of English would be much larger than.
Yeah, just make it an apology. Sorry, I didn't have time to do my homework assignment. Please forgive me. There's your 4-page paper. I always grab the coffee with the wrong hand when I'm over electronics. I have bad shakes in my hands and I slosh. Getting too old. Okay, so punchline here is that larger bases allow us to represent big numbers in a more compact form. Okay, so that might be our rationale for bases beyond 16, let's say, for a moment. Now, as it relates to computer science, though, we obviously use binary because of digital logic, on, off, 0, 1. Binary is compatible with the way computers work. Now, it's going to change here. Well, not completely change, but somewhat change relatively soon. Microsoft recently had that announcement about their programming languages for quantum computers, which I guess the simplified version of this is quantum computing deals with 0 or 1 or both. So it's kind of a third state, which is similar to the discussion we're talking about right now. You can actually represent more data in 3 states than 2, right? But then also changes the complexity of how you ask questions. Because now a Boolean expression is no longer a true or false. It's a true, false, or maybe, I guess. You know, kind of a third thing. But it'll be interesting in any case. But point is, we use binary because it's compatible with digital logic. On, off, 0, 1. We use decimal because it's compatible with us. 10 fingers, 10 toes, we like the counting stuff. Compatible with us. Why do we use octal? Good.
The next, like, power of 2.
Well, it is a power of 2. So it kind of makes sense because it's a power of 2. You might not know the answer to this. I don't remember. Did I have you do a paper on octal decimal stuff last semester?
Yeah.
Okay. Yeah, then you should know this. So it is a power of 2. So why is that beneficial to us? Yeah. It's the same thing goes with hexadecimal. Any of these powers of 2 can be grouped. So for instance, we can, if we want to take a octal number, let's say we have 614 in octal. And I want to convert that to binary. We can go through the motions of doing that, but actually the conversion of that is pretty easy because you can do the legal digits, the legal octets in octal is 0 through 7. How many bits do we need to represent a 0 through a 7? 3 of them. Okay, so a 6 would be a 1 in the 4's place, a 1 in the 2's place, and a 0 in the 1's place. A 1 would be a 0 in the 2's place, or 0 in the 4's place, a 0 in the 2's place, and a 1 in the 1's place. A 4 would be a 1 in the 4's place, a 0, and a 0. That's the binary version of 614. Does that make sense? So it's an easy conversion for a human, as well as we could write a program that does groupings like that as well. Okay, so we're going to look at that here in a minute as well. If I have a, well, my favorite is BAD. That's my favorite hexadecimal number, which is 2989 in decimal. But if we were to convert from base 16 to binary, this is actually what? This is a 11 followed by a 10 followed by a 13. C, D, right? 10, 11, 12, 13, yeah. So the B is the 11, the A is the 10, the D is the 13. Well, 0 through 15, how many binary, how many bits do we need to represent 0 to 15? 4 of them. So we'd say, what is 11 in 4 bits? What is 10 in 4 bits? What is 13 in 4 bits? So an 11 would be we have the 1's place, the 2's place, the 4's place, the 8's place. So we'd have 1 in the 8's plus 0 in the 4's plus 1 in the 2's plus 1 in the 1's. That's my 11. My 10 is a 1, 0, 1, 0. That's my 10. And then 13 would be a 1 in the 8's, 1 in the 4's, 0, 1. So that's the binary version of BAD. Make sense? And if we wanted to throw 2989 in there. So this is the decimal version of it. This is the binary version of it. This is the hexadecimal version of it. So this kind of proves that thing where hexadecimal, being the largest base, is the most compressed, smallest footprint. Decimal has a little bit bigger footprint. Binary has a much bigger footprint. Make sense? But those grouping conversions are only going to work for those powers of 2. So that's why we've specifically picked those for our kind of convenient bases in computer science. You know, it's easy to kind of fall back onto this idea that, oh, well, we need a larger bucket to store things. So that's why we typically use hexadecimal values on our computers for like memory addresses, right? Well, why do we do that? Because we want to have a lot of memory. And what's a memory address inside your computer? It's a street address, just like in real life. As soon as we throw the word memory in front, it gets way scarier. But the reality is it's just a street address. Except in our computers, our streets we don't have all these interconnected streets. We have just one gigantically long street that everybody lives on. This person lives in house 0. This person lives in house 1, house 2, house 3, house 4, house 5, so on and so forth. All right, so we need to index those houses. And depending on the size of value we are going to use to index those houses, that tells us how many houses we're allowed to have. So, this maybe goes back a little bit, but do we remember when most of you probably used Windows 95 at some point, right? So do we remember back in some of the early days, you would go to format. So this is going to be something that's more IT specific for some of you, but it's still very related to computer science. If you went to, let's say you bought a 4 gigabyte hard drive or a 6 gigabyte hard drive, like you used to be able to buy hard drives of that size. If you were doing that, you could not format them to 6 gigabytes. You would have to create 3 partitions, each of them being 2.1 gigabytes. Anybody remember that? Nobody ever experienced that?
We really think we were formatting hard drives.
No, some of you might have. Well, no, I mean, it went on for longer than that. It wasn't just Windows 95. Yeah, Windows 95 was out for a while. So before it ever got beyond that. So, I mean, this could have been like when you were like 11 and stuff. Okay, but in any case, that was a true statement. is you couldn't have a single partition bigger than 2.1 gigabytes. Wouldn't that be problematic today? I mean, we have single files we download that are bigger than 2.1 gigabytes. So now you're saying back then we couldn't have had a single file wouldn't have fit on our largest possible hard drive. Even if you had a 50 gigabyte hard drive, it was broken into 2 gigabyte baskets, specifically 2.1 gigabyte baskets. Does that 2.1 sound familiar for anything we've talked about in here? 2.1 billion something or other? What is that?
That was one of the,
Size of integers.
yeah.
Size of integers. So integer is plus or minus 2 to the 32nd power, right? So plus or minus 2.1 billion. So 32-bit memory system allowed us to have a maximum hard drive size of 2.1 gigabytes because of the way now we start getting down into what's the block size on a hard drive. I don't want to go that deep into it, but in any case, we only have so many buckets that we can index. Once we run out of places to count, we're out of stuff. So we can only have 2.1 billion things on that hard drive. And now we need to decide, well, what's the smallest thing that we can store? And that's the size of our drive, because we can only index 2.1 billion things. If we want a larger drive, then what do we get up to? That's when we start looking at 64-bit, which is something in the ballpark of, I think, 16 terabytes or something like that. Now you start getting, and so what you started seeing is these operating systems started having aspects of themselves operating at higher bit orders. So for instance, you might have a Windows 98, for example, was still a 32-bit operating system, but had a 64-bit memory manager to allow you to have larger chunks of, actually 64-bit disk manager. Still had a 32-bit memory manager. So this is probably something you've run into. If you had Windows Vista, is this more in our ballpark? We've used Windows Vista. The 32-bit version of Windows Vista, what was the maximum amount of memory it would address? Because back then, 8 gigabytes of memory existed. You could put 8 gigabytes of memory in your computer, but it would only see 3.5. It could address 4, but it would see 3.5 gigs of RAM. So you put 8 gigs of RAM into your system, and your operating system says you have 3.5. That doesn't make you that happy, right? The only way you can see your full 8 is if you installed the 64-bit version of Windows Vista, which actually had the next order up for its memory manager, for how it represented the counter. It couldn't count more than 3.5 gigabytes. 4 gigabytes is the reality. Does that make sense? So those decisions we make mean something for our capabilities. You could have all the space in the world, but if you don't have big enough numbers to index it, you're not going to be able to find stuff. So it's easy for us to think about something like hexadecimal and say, oh, well, we just needed to store our big memory addresses in smaller footprints. Otherwise, the numbers would, if we were looking at a memory address in binary and we were talking about, house 2 zillion, well, it's going to be a gigantic binary number that takes up a lot of physical space. So what if we encoded it, if you will, in hexadecimal and then turned it back into binary when we needed it? That made much more sense because we're fast at computation. We only have so much physical space laying around. But why didn't they pick base 17 or base 18 or base 19? Well, they picked base 16 because it was also compatible with the groupings. So what's going to happen at some point in the future? Some point in the future, if we decide that we really can't, our hard drives haven't caught up yet. Maximum size of our hard drives haven't caught up with the maximum addressable space of a 64-bit disk manager. But eventually, we would presume it would, right? I mean, a couple of years ago, biggest hard drive size was, 2 terabytes? Now I think you can buy a 6 terabyte hard drive is a single drive. Now we're actually kind of taking a step backwards in size because we're starting to transition over to solid state. But solid state's already almost caught right back up, right? The biggest issue now is price. But it's even gotten significantly more reasonable from the price point as well. But eventually we assume we'll catch up to the, we'll be at 16 terabytes and like, oh, wait a minute. If you're going to buy a 25 terabyte hard drive, you're going to have to partition it into a 16 terabyte piece and a 9 terabyte piece. That'll become, a next problem. So then we decide, well, how do I even operate off 16 terabytes? I might have one file I download that's bigger than 16 terabytes, which seems ridiculous to us today, but having one file that was 2.1 gigabytes seemed ridiculous to somebody in 1995 as well. So it's, time catches up to us, I guess. Okay, so this grouping technique only works in those powers of 2. So we're going to write a more generic version for converting for any bases. Okay, so base to decimal, we have the value we're taking in as well as the base it's currently in, which is our radix. We'll start at the end of our value, walk to the beginning of our value. Each time through, we will pass in our character at the particular bucket in our value into getInt from char. So this guy would give us a 10 for an A, an 11 for a B, a 12 for a C, so on and so forth. It'll give us a 2 for a 2. So this guy will convert. And we could have even just put this code down in here. Maybe would have looked a little bit scary, but that's effectively what we've done here. We're just calling this really short function up here. So getInt from char, multiplying it by the current place, adding it to our sum. Each time through, we'll say place is equal to place times radix. So place always starts off at 1, no matter what base we're looking at, and it always goes up by whatever the base is. So this code right here, well, all-encompassing, is a universal converter. We can pass it a string in any base. In base 37 or less. Dr. Walt is logged into a Mac. I forgot I log out of iCloud on the Mac I gave him the other day, and I just had it pop up. So in any case, as long as I pass it a base of 37 or less, this will spit out the decimal version of that number. Okay? Now, things get a little bit more interesting on the other side. If I want to change my decimal to binary to be decimal to base, and I take in my decimal, and then I take in the radix I want to convert it to. I could still do this extra little check. If the decimal is 0, it doesn't matter what base you're talking about, the answer is 0. Otherwise, we'll start our answer off. We'll keep whittling it down as long as decimal is greater than 0. Each time through, we're going to mod it not by 2, but by our radix, and tack that onto our answer. And then we'll divide decimal by our radix. But now this piece of the code right here is going to be problematic sometimes. Under what conditions will that be problematic? When I have something that has a remainder of 10, I don't want to have that 10 tacked onto my string. I want to have an A tacked onto my string. So I need to be able to convert that remainder into the appropriate char. So I want to have a function static char. Let's call this guy remainder to char. And this guy will take in an int val as a parameter. So I want this guy to return a 1 for a 1, a 3 for a 3, an A for a 10, an F for a 15, so on and so forth. So we saw that we could do the mapping one direction using index of. But now I want to go the other direction. What's the inverse of index of? Do we have another tool sitting in the toolbox that at first glance doesn't necessarily seem directly related, but in actuality is the inverse tool? Charat. I can take this exact same line, well, almost that exact same line. So I had a whole alphabet, and I can say, give me the charat bucket val. Charat 0 is 0. Charat 8 is 8. Charat 10 is A. Charat 15 is F, so on and so forth. Make sense? So now I'll call, before I just tack it onto my answer here, driver.remainder to char. So I'll go ahead and look up that remainder in that function real quick to give me the appropriate symbol. Make sense what we're doing there? Okay, so one thing that one of the reasons I like to kind of look at this, and I know we did something like this last semester, but now we have some new string functions to work with, right? So this kind of let us approach, well, first of all, you already know I like conversion stuff. So we get to practice more conversion stuff. So if you were bad at it before and you're still bad at it now, at least you hate yourself a little bit more at this point. So in any case, one thing hopefully we're seeing here, I think I mentioned last class, I've mentioned it several times over the last year or so, is that we, as programmers, we try to be like MacGyver. And we've all seen that show at some point. I think it's actually made a comeback. But you know, the premise of MacGyver is he was this guy who every single episode got into some sort of trouble. And he was stuck in some place and only had a very limited number of supplies sitting around him, and he had to solve whatever problem he was confronted with using only what's laying around. You know, building an airplane out of a lawnmower and some wood in a garage or something. You know, some stupid stuff. Mythbusters did a thing before, like tried to could MacGyver actually have done what he did in the show? And I was actually very surprised. I thought everything on TV was true, and apparently some of the stuff was not. But in any case, we're at the mercy of what tools we have in front of us. I mean, we have several limitations on a given day, right? Okay, so if we're extra tired, maybe we're not thinking quite as clearly, so we might not come up with the best ideas. Yeah, that's you today. Yeah. So yeah, it's me today too. I've been chugging the coffee for a while. I had a rough night last night, as all Christian school professors have. So in any case, we have we have various tools that we have laying around us whenever we're solving a problem. We have the tools that we're supposed to have learned, right? And then we have the tools that we might remember at the time. Okay, so right now, things are pretty fresh in our mind. We kind of know about the charat. We kind of know about the index of. We know about those guys. But we're not always going to recall those things. So sometimes we're going to end up having to write a tool, and we'll get 80% done writing it and realize, oh, I kind of already had this. But you got some good practice, right? You're not going to always remember. I mean, this is the same thing we deal with in real life. If you are fixing some stuff around the house, and I mean, we all know that over the years you collect a zillion tools in the garage, right? But we don't remember what's out there. I mean, that's why everybody has just multiple tape measures. Can't find a tape measure one time, you buy a tape measure. Next thing you know, you got 9 tape measures. Same thing with hammers, same thing with screwdrivers, same thing, nails as well.
Tape measures and screwdrivers are like tissues.
Yeah.
You have one in every room.
One in every room, and then you lose that, and then cats find them.
Right.
So the same thing is true with programming. Over the years, you're going to learn all these different skills. You're going to learn all these different tools. And some of them are going to stick because you use them often. So for example, I promise you, as long as you stick with programming, you're not going to forget the for loop. You're going to use that pretty often. All right, you know, you're going to be okay with that. All right, but some of these other tools you might forget. You haven't used it in a while. It's like, oh, what was it again? What was the name of that function? That's why we have practiced reading the documentation. But right now, we have a relatively small toolbox in front of us, and something I encourage students to do is write down the tools they have in their toolbox. So you have a nice little checklist. So then when you're going to solve a problem, you can kind of look at your checklist and say, okay, what do I have? What tools do I have available? Okay, and another thing I do is I say when you're solving your homework assignments, solve it in terms of the tools you currently have access to. So I promise you, there is a built-in mechanism for converting binary numbers significantly easier than we just wrote. But then we wouldn't have had the joy of writing it ourselves. Right? I mean, you can build a house with hammer, nails, and wood. You don't need to hire a contractor. It's far less. All right, so think about the tools you have available to us, but the nice thing with this char at and the index of is we look at them and they seem so simple in and of themselves. They don't do that much, but we actually see we can solve some pretty powerful problems with them. Same thing's true with the modulus operator. It doesn't seem all that powerful. I mean, it's third grade math, right? Long division with the remainder. Yet we use it fairly often in computer science to solve problems that are actually pretty important. All right, so third grade math actually was fairly useful. Okay, so questions about any of that stuff? So let's circle back here to our dice, and I want to show the pass by value stuff here. So I'd thrown in an error. So here I'll go ahead and I'll throw you these upgraded functions into into Slack so I can dump them. Okay. All right, so this is kind of what we were looking at last time. We had created a simple little dice object. We set its sides variable, its field, to 5, and then we print it out right here. So we should see 5 get printed out. Now I'm going to create a function. That's going to take a dice as a parameter and sets the sides for that dice to -1. So I'm going to call this function. I'm going to pass it a dice object. It's going to take whatever that dice object is, and it's going to change the sides. I'll go ahead and print out the sides in here. And we would expect it to be -1, correct? So create my dice, set the sides to 5, print out the number of sides. That's going to print out a 5. Pass that dice that has sides 5 to change me. It comes in to change me under another dice named D. If this that confuses you, we can just change that to cat. Because they are, in fact, different variables, even though they had the same name. Okay? So here's a variable named cat, which will represent D that gets passed into it. We're going to go ahead and change cat's sides to -1. In fact, if you want to see that it was 5 before, why don't we go ahead and print it out before we change it, then print it out after we change it. So this will print out the original number of sides, which was 5. Then we'll change sides to -1, prove that we changed it by printing it out again, which should be now a -1. So the output of this program right now should be 5, 5, -1. So far, so good? So then the question is, when I come back to my code here, what will the output be? After this function has been called, and I'm back here where this is my dice, when I go to print out sides, will it be 5 or will it be -1? What do you think? And why? Think it'll be -1? Why?
Because it's calling an object, not an instance.
Think you might know what you're talking about. What do we call it, an object?
Well, because like change means it's a static, so it's not like an instance.
Yeah, that has nothing to do with it. Yep. It has more to do with this guy right here. What he's taking in. But he thinks it's going to be a -1. And I think he's right. There's a -1. So now the question is why was it a -1? What is D? D is a variable, and it holds a value. What kind of value does D hold? What will print out there? I created a variable named D. I set its size to 5, and then I print out D. What kind of value does D hold? Well, what did we put in it? Okay, so we think it'll print out an int here? So we know variables always resolve to their most local definition. So we know that D right here is this variable right here. And it will resolve to the value stored in that variable. Now in this case, we only have one integer that's stored inside of my dice, but I could have 20 integers in there, right? Nothing keeps me from putting more stuff inside of there. What kind of value do objects hold? They hold memory addresses. This is a pointer to where my dice lives in memory. So if I print this out, I'm going to see a crazy looking memory address. Hexadecimal number right there. Make sense? Now we're working in a Java virtual machine, which is why Java creates their own like unique memory addresses. So that's the dice at that memory address. So what's a memory address? Now, let's create the exact same model we had before. Static void change me to. Have this guy taken an int I. Little system.out.println I. Then we'll say I is equal to -1. Then we'll print it out again. So I'm going to say int sides is equal to 5. I'll go ahead and print out sides. Then I'll call driver.changeMe2. I'll pass that sides. It's going to receive sides, print out a 5, change it to a -1, print out a -1. What's going to print out here? Back to a 5, or still a -1? It's the exact same example we did a second ago, or a couple minutes ago, except we're working with an integer primitive type this time instead of an object type. So what will this line right here, the line I have highlighted, print out? We know this line prints out a 5. We know we're passing our 5 into this guy. So we'll print out the 5. Then we're changing that variable to -1. Whatever variable is passed in here has now become a -1. Print it out again, it's now a -1, proving it has changed. Now when I return to my program up here, and I go to print it, you think it's going to be a 5? Okay, I agree with you. It's going to be a 5. There's my 5. So 2 seemingly identical examples with 2 different behaviors. Why did this one not permanently change? What kind of value is sides? Sides is a variable of type int, so it holds a value. What's the value stored in sides? Yeah, it's an integer literal, i.e., what's important to us right now is not a memory address. I promise you under the hood it does live in a memory address somewhere. But primitive types resolve to the innate, the internal value of the memory address rather than the address itself. So so this guy would be called, this is pass by value. Sometimes it's called pass by or copy. We gave it a copy of the value stored in sides. So we handed it a 5. And they could do anything they want with that 5. It's not going to impact the 5 that we had here because we gave them a copy. Now up here, when I handed them D is an object. What I actually handed them was the memory address where they can find this object. Okay? Example I usually use or something along these lines is if I have if you ask me for a quarter and I have 2 quarters in my pocket, I reach in and I throw you one of the quarters. Made a copy of the quarter. And you go and melt the quarter down somewhere. It's not going to impact the quarter that's still in my pocket, correct? So I gave you a duplicate quarter. But if I give you the address to my house and you run over there and spray paint my garage, I'm going to see that when I come home, right? Okay, so that's the difference between pass by value and pass by address. When I gave you the memory address, the location where my garage is, I passed you the address. You're going to, we're both working with the same place in memory. So any changes that happen here will be realized by this guy. When we're passing by value, I'm giving you, you're creating your own new memory location. I'm just saying, here's your quarter. Here's your 5. Work with it, do whatever you want with it. I'm still dealing with this guy up here. Does that make sense? A pretty important concept for us. All right. So now let's look at constructors. So what I'm actually going to do is I'm going to make that variable private. Now, by making that private, I'm not going to go too far into that for this exact moment, but we see now we're not allowed to do something like this. We can't say d.sides anymore. We cannot directly access that variable because we've locked it down inside of our object. All right, so for right now, we're going to make all our variables private. until this is kind of like the static argument. Make them all private and then give access as you need. So now we're going to make a public constructor. Constructors in Java must always have the same name, case sensitive and all, as the class name. Now, if you remember from Python, constructors were called init, right? We had init in front of it. Well, Java, it just shares the name as a class. So we're going to say, we'll have this guy take in an int s, and we'll say sides is equal to s. And what this now allows us to do is it allows us to, we're no longer given the no argument constructor that we had before. So now it doesn't like this line either. It only gives us that no argument constructor that does nothing to support the new keyword if we don't write a constructor ourselves. But we just did. We just wrote our own constructor. We know it's a constructor because it shares the name with the class name. So now when I create my dice, I'm going to go ahead and pass it in a 5 for the sides. All right, so I gave it the number of sides. That's going to come in as s. I'm going to set sides equal to s. Now, realistically speaking, I don't really like this variable name s for my input for dice. I mean, it's not descriptive. I'd really like to call it sides. This is the number of sides for this dice. So then I will say sides is equal to sides. But then the question is what am I talking about there? What I really want this to mean is I want the sides here on the left to be the sides up here, and the sides here on the right to be the sides right here. So this is where we see the this keyword, which is like the self keyword we learned last semester. So this dot sides, that is the sides variable owned by this object, this instance of the object, will equal the most local definition of sides I can find. And the first place he finds sides is right here. All right, so this dot sides is equal to sides. It also has the advantage of if you do this dot, you don't have to worry about misspelling. Okay? Now, because I've made this guy private up here, if I want to get access to the sides, I need to give myself what are called we have things called getters and setters. Okay, so getters allow you to get the value of a private variable. Setters allow you to set the value of a private variable. In this case, we just want to get the value of something. We can write our own, so I'll go ahead and just write it real quick. So I'm going to say public int get sides, and this guy will just return this dot sides. So I've given myself a function here called get sides that returns an integer, and all it returns is the value of this dot sides, which notice it's happy enough with this one because private variables can only be accessed inside the class in which they were defined. So I'm inside the class called dice. This guy's a private variable of dice. Am I still inside the class dice down here? I am, so I can access this dot sides. Out here, though, I am not inside the class called dice, so I cannot say d dot sides. Instead, I can say d dot get sides, and that will get me the number of sides from that guy. Effectively, this is read-only access to sides. Because if I could access the field directly, I could change it. I could set its value, and I could also get its value. Now I've only written a method to get the value that lives in there. That make sense? All right, so let me delete some of these things here. So I'm going to come up top in driver. So I'm going to introduce a new object to you that you're going to have to use for your homework. I'm going to import java.util .star. That's fine. Good enough. And actually, Eclipse will do this for you, so I'll show you what Eclipse would do if you didn't do the pre-import. So if I just come down here and I say, okay, I want to create a random R is equal to new random. Eclipse is going to notice, oh, I haven't heard of something called random. If you highlight over that, it's going to say, oh, import random from java.util. So it'll go ahead and import it for you. Okay? Or you can just import java.util.star, which just says, give me everything in util. Or import java.util.random if you knew that's exactly the thing you needed. I usually just let Eclipse do it for me, but, you know, choose your poison. So now we have our random, and I'm going to show you one method that you're allowed to use for your homework with random. Okay, there's actually two versions of this method. You're only allowed to use the one that I'm showing you. Okay, it's a very important part. So I'll just write a little for loop here. Int I is equal to 0, I is less than 10, I plus plus. And I'll do system.out.println r.nextInt. So we have a method that lives inside of, it's an instance method of the random class. We know it's an instance method because we're calling it with r dot. We're using an instance to call it. And this guy returns a random number, a random integer in the range of all integers. That is between -2 billion, -2.1 billion, and +2.1 billion. So this will show you 10 random numbers. I just threw it inside the loop. Make sense? So this is the only version of NextInt you're allowed to use. There's another version that you are going to wish you could use. I'll show you next class. But for your homework assignment, we want to add a method called roll that rolls the sided dice some number of times and returns the sum of the rolls. So if I want to roll a 6-sided die 3 times, I would call my roll, passing it a 3, and it would roll it 3 times individually, sum them up, and spit the number back out. Go ahead. No, because it's sided dice. Yeah, however many sides you built this dice. So I can build 3 different dice. I can have a 20-sided die, I can have a 6-sided die, I can have a 3-sided die, and then I can tell each of those to roll itself some number of times. That's fine, it'll fit inside of int. All right, questions, comments, concerns, bribes? All right, I will see everybody on Tuesday.